ablation using computational model.
Thank you very much. So for those of you who are expecting Pranav Bhagarath, then apologies, but he couldn't make it, so Steve asked me last minute to step in. So hopefully the talk that I'm going to be giving today is at least in the spirit of what Pranav would have presented. So it's really a bit more on the other scale to what a lot of things that have been presented today. For a start, it's focusing on one quite specific thing, which is the specific problem of guiding VT ablation using modeling, as we can see here, but also probably a bit more towards the actual, sorry? Yeah. Trying to actually do things more directly on the clinical side of things as well, or at least attempting to move in that direction a bit more. So there's two main things that we're going to be talking about today, something that's a bit fast and something that's a bit more simple. So hopefully everyone, or most of you at least, are aware of the main problem with VT ablation. So it remains very difficult to try to identify and actually to target these diastolic slow-conducting isthmuses, which are what are responsible for actually sustaining reentrant VT in the majority of those cases. And specifically what we want to do is we want to try to target the entrances and the corresponding exit, or the corresponding exit sites, which therefore form the targets of ablation. Now, substrate-based ablation just tries to kind of bazooka the whole scar area, but non-substrate-based ablation usually requires VT induction. And that can be very difficult. It can be quite dangerous. Often you can't induce at all. Or if you can induce, then often you don't end up inducing the right VT anyway, in terms of the clinical VT. So it doesn't do much good anyway. So these procedures ultimately end up being very long, very problematic, and then the recurrence rates are actually unacceptably really quite high. So about 50% of people end up coming back after about a year with the same VT that they came in to start with. So in this context, an in silico approach, which tries to use kind of a patient-specific modeling idea to try to guide VT ablation, particularly if we could do that pre-procedurally, would actually seem really quite attractive. And a number of groups around the world have been attempting this for quite a few years. And here the overall concept, obviously, I'm going to refrain as much as I can from using the word digital twin, so I'm going to refer to it as patient-specific modeling. So we take kind of anatomical imaging data, we create biventricular models, sometimes including the torso as well. And then we basically use these models to try to basically use them to do kind of aggressive VT stim protocols. So we stimulate virtually all over the heart as much as we can to induce as many VTs as possible. And then it allows you to just use the model to see it and to visualize the VT circuit, and then we can identify the target. And then this target can potentially be incorporated into the electron anatomical mapping system to try to guide ablation during the procedure as well. So in attempting to do these aspects of this pipeline that I just showed, because it seems very easy when I just present the whole thing in one go, we've uncovered quite a number of kind of considerations or challenges associated with this, which we think is really kind of limiting the actual translation into the clinic. And the first of this revolves around the fact that many of these models are kind of based on monodomain or bidomain representations of electrophysiology, which if you want to remove any issues with numerical artifacts, usually requires really quite fine resolution grids. And so these end up being really very large, computationally cumbersome models. And they can take, just for one heart, for the whole VT stim protocol, it can take 1 to 2 days on an off-site HPC, which might not be in keeping with the kind of clinical workflow. It's not quite as much as Matteo's 5 centuries, but it's still quite a long time if you're thinking about a clinical workflow. The other thing is functional personalization. So often we just take off-the-shelf literature values for the functional parameters that control ionic conductances or tissue conductances, which govern the dynamics and the inducibility of the VTs. And because these aren't on the whole patient specific, whether the results that we get actually reflect what's going on in the patient is potentially of a concern. Potentially the most important thing, though, is actually reconstructing not just the anatomy, but the scar substrate from the imaging data. So because most of these VTs rely on these reentrant pathways, these are usually only a few millimeters in diameter. So if you're thinking about different imaging modalities, different segmentation methods, different thresholds, the presence of artifact, reconstruction methods, all of these things come together to mean that whether we can or not, we can recreate or reconstruct these really, really fine diastolic isthmuses, which are absolutely crucial in driving the VT, is often quite hit and miss when we're putting these models together. And if you don't end up with the right isthmus, then your model's pretty much useless. You're never going to get the right VT that this person is presenting with. So the two projects that I wanted to share with you today, at least in some way, try to at least think or try to address some of these considerations. And these for me are really the definition of collaborative projects, with Gernot Planck, who's going to be giving the keynote talk tomorrow and possibly touching on a few of these areas as well as our clinical collaborators in St. Thomas's, led by Aldo Rinaldi, and particularly John Whitaker, who in the last couple of years is really pushing the VT program where we are. And on the left, we kind of have the fast, and on the right, this is more the simple. So the first of this, the one I'm going to be talking about, is the one where we're trying to identify clinically relevant VT circuits, but in near real time. So termed Vita, which is the name that my postdoc came up with, and it's kind of stuck. In essence, it's more of a simplified approach, and what we do is we use reaction iconal pacing. So this allows us to use much more coarse, much more computationally lightweight models, which means it's just a lot faster. And what we do is we pace in multiple places, and every time we pace, we keep track of the wavefronts, so the isosurfaces of the wavefronts. And every time those wavefronts split up, these then define the entrances of the isthmuses, and then when they recombine, they then define the exit sites of these isthmuses. So once we have, for example, the exit sites, this then defines our starting line. This is our starting line for unidirectional block. We then do a second iconal solve, which then allows us to recover the entire reentrance circuit, and then we can get from that the cycle length and things like that afterwards. We can then make use of the tools developed by Gernot and his team to automatically go from these circuits right the way through to simulating the ECGs and also simulating potentially the device EGMs that will be sensed by an ICD as well. And these are really, really, really crucial when we're thinking about validating and comparing about clinical recordings and the VT that these patients present with. So testing Vita on a preclinical cohort, these are just some porcine infarcted models. We did a kind of a like-for-like comparison against conventional monodomain VT stim protocols, and we showed that fundamentally our Vita method is basically identifying the same anatomical VTs, but just in a fraction of the computational time. We do hold our hands up though, and we do say that Vita does not identify the functional VTs, it only gets anatomical VTs. So for example, we would not have got this spiral wave-like functional VT that you'd get from the monodomain model. But again, I'd stress the huge, huge delicate dependence on the inducibility and the overall dynamics of functional VTs like this on the parameters that you put into the model, which on the whole are just based on the literature and they're not patient-specific in any way. So current work which we're doing with Vita, primarily we're trying to clinically validate it, and I'll say a little bit more about that later, but we're also focusing on trying to make use of its speed. So fundamentally the main functional parameter that goes into Vita, or the only functional parameter that goes into Vita really, is the conduction velocity, the conductivity of the tissue, which ultimately governs the cycle length. So potentially we could look at personalizing this globally from a 12-lead ECG, from the QRS, or we could look at, and we're interested in trying to come up with ways to kind of intra-procedurally update the conduction in a heterogeneous manner from catheter measurements during the procedure so the models can be updated and rerun as the procedure's going on. Really importantly, as I alluded to before, there's this uncertainty in the anatomical substrate of the scar when we reconstruct it from the imaging data. Now, because Vita is so fast, it actually opens up the possibility to be able to reconstruct multiple different instances of anatomical models with different scars that have been created from different segmentation methods, different thresholds, for example, and then we can run Vita over all of these models simultaneously, producing these ECGs, which we can then map back to the clinical ECG that the patient presented with and see which one fits the best. And that will give us a bit more confidence that the model that we're using actually matches the substrate of the patient themselves. Alternatively, we could actually think about using the data in a different way. So instead of throwing it away, actually combining all of the data from the different models, the different Vita runs, potentially the different conductivity parameters, and actually combining it all into one model and one representation. And this is trying to move a little bit away from saying, I've got one model, I'm going to do one simulation run, and I'm going to get an exact XYZ ablation target that I'm going to stake my life on. And I think we need to be a bit more aware of the uncertainty of the data that goes into constructing these models to actually combine data from multiple runs and to produce more of a probability or a heat map to guide the clinicians to the best place to start routing around in instead of giving them an exact XYZ. And again, we're going to be thinking about validation. So I couldn't really talk about Vita without talking about our work on risk stratification, which I'm really, really interested in personally. So this is work that we do with Professor Sanjay Prasad at the Royal Brompton and his colleagues. And Sanjay, for those of you who know him, has absolutely incredible clinical data sets, huge cohorts that he follows up for huge, huge amounts of time. So this is working with this ischemic cardiomyopathy cohort, and these patients were followed up for about 10 years. And there's huge amounts of follow-up data. So I think I counted the other day, and each one of these patients has got a spreadsheet with 217 different columns in for every single piece of data you could possibly hope to have from this particular patient, as well as what we're interested in, which is the follow-up data. So fundamentally, we use this MRI data to reconstruct biventricular models. We then map the information from the scar across. This is working with Alistair Young at King's using some of the methods that he's been developing. We can then take all of these models, these 400 or so models that we've got, we can then run them directly through Vita. And again, this is only possible because it's really fast. If we wanted to do this with a monodomain approach, this would be taking a year and a half to run on an HPC. We can set this going, these 400 patients on my desktop, and after a long weekend, we can come back and we've got all of the data. So Vita already kicks out really important biomarkers, if you like, about the number of VTs and metrics about their cycle lengths. And then these biomarkers then can be then used in association with the follow-up data, with the event data, in, for example, standard Cox regression models to try to probe for associations of these biomarkers with event data from the patients. And this is very preliminary work. It looks like some of these things are seeming like they might be important, but there's still a lot of work that we need to do in this regard as well. So the second project that I wanted to talk about is the simple aspect of it, and this is our project which we've termed in silico pace mapping. And again, this is working with Gurner and particularly with numerical as well, and also our clinical collaborators, John and Aldo in the lab, are really, really important in this as well. So for those of you that aren't aware of the concept of pace mapping, so pace mapping is when you have an ECG of the VT, and then you have a catheter in the cath lab, and you basically just go around the heart pacing. And every time you pace, you get a breakout and you get a 12-lead ECG. And you just correlate that with the 12-lead ECG of your VT. And the idea is that the morphology of the QRS matches when you're at the exit site, and it has almost the opposite morphology at the entrance site. So this is hopefully shown in this kind of simulated example here. And this is because as the activity comes through the diastolic isthmus, it kind of breaks out in a very similar pattern to it would do if you just stuck a catheter at that exit site and paced. So that's the overall concept of pace mapping. And to be honest, the idea behind our in silico pace mapping project was quite embarrassingly simple as well. It was basically just to take an image-based computational model, including the torso, and then just to pace the heart in thousands of locations. Every time we pace, we just get a 12-lead ECG. For each one of these ECGs, we just correlate with the presenting clinical 12-lead ECG. This gives us a correlation coefficient, which is a number, which we then map back onto reconstruct a correlation map, or a pace map, which is basically just what they do clinically, but we're just doing it in silico. So as I mentioned, one of the main limitations of either these full monodomain approaches or even our rapid Vita approach is the really delicate dependence and the huge reliance that they have on the imaging data and the reconstruction of these scars and whether or not you can reconstruct the isthmus or so. The potential beauty of in silico pace mapping is that we're not actually trying to simulate the VT at all. We're not trying to simulate the circuit or the dynamics or anything like that. All we're trying to do is simulate pacing. And so potentially these models might not be, or this approach might not be as sensitive to the specifics of how we reconstructed the scar substrate as a method that actually tries to simulate the VT itself. So I won't dwell too much on this slide, but this is very preliminary work, and this seemed to be the case. So here we just took some models. We had models which had all of these fine isthmuses. Then we had models where we basically just filled in all of the critical pathways, so the scar just looked like this big blob. And then we basically just had a model without any scar at all in it. And for each of these models, we did our in silico pace mapping approach, and we showed that although there was a difference, obviously we're doing a bit worse when we don't have scar. We have this kind of model of scar with the filled-in isthmus, but we're still doing quite a good job of getting quite close to the exit site. And obviously, the ECG does change if you have scar, if you don't have scar, if you change the amount of scar, but still the site that's most likely related to the exit site is still close to the exit site, whether you have scar or not, because you still have that same kind of breakthrough pattern. So in silico pace mapping using 12-lead ECG data is potentially quite interesting, but what we're really excited about is the potential of whether we can reconstruct an in silico pace map using EGM data. So these patients have got, because they're coming for an ablation, about 90% or so of them have got an implanted device. These implanted devices have already got recordings of their clinical VT, which is why they're coming in for the ablation. So we're trying to utilize and try to leverage this data. So the idea here is to basically do exactly the same as we're doing with the ECG approach, but here, instead of simulating ECGs, we're just trying to simulate the EGMs that would be associated with that VT that the device would detect. And then we just correlate it, instead of with the 12-lead, we correlate it with the recording from the device EGM. And again, we just reconstruct the pace map in a similar way. So the concept of using ICD data to guide VT ablation isn't necessarily novel on its own. Potentially it's quite useful because you could be a bit more sure that you're targeting the clinical ECG. If we're doing this in our context, we would be able to do it entirely pre-procedurally. We wouldn't have to induce VT in the lab because we've already got these recordings on the ICD. However, we might be a bit more limited with the data because here we're dealing with potentially 2 to 3 sensed EGMs instead of 12 lead from the ECG data. We did show in a preliminary study from my former student, Sophia, that actually if we were able to leverage these multipolar devices, so for example CRT-D devices, which actually pace the heart with multipolar catheters, you can get out more sensing vectors. If we're able to leverage that amount of more information, then we might be able to do almost as good a job at identifying the exit site as we would do with a full ECG, a full 12-lead ECG. So we are actually trying to validate this, and this is where the validation of Vita also comes in. So we've been lucky enough to get some money from the British Heart Foundation to do a validation study on 25 VT ablation patients. So here we're not just trying to see if we can localize the VT exit site, because we only get one of these for each of our 25 patients. But every time they produce a pace map in the clinic, which is what John and Aldo do as part of their procedure, they're acquiring 20 to 40 sites where they know where the catheter is, because the Carto system tells us the exact XYZ of the catheter, and we know the corresponding 12-lead ECG. So we're also going to use our model to see if we can locate these focal beat, kind of these focal-like VTs from the known locations of the catheter in terms of this, so we get far more data for each patient. And we're trying to do it both on the ECG side and also the EGM side as well. And luckily enough, this also provides the perfect data to be able to validate Vita as well. So this is very, very preliminary data literally obtained from John in the cath lab in the last few weeks. So here we go through the standard procedure. We have the imaging data, we create models, we have a torso, we can simulate the ECG. We take the model, we paste in thousands of locations. Here we're just starting off doing the ECG problem. So we simulate our ECGs. Then we have the Carto data. So now one of the main problems here is registering the Carto data to our BI-V model. So here we use the aortic cusps, which comes out from part of the Carto procedure, so we can register, do the best job we can to register with our BI-V model. And then this is just showing an example for one of our pacing sites, which you can see in purple. Then I've highlighted it in yellow, and that's the clinical 12-lead ECG for that particular site. We then take that clinical 12-lead ECG, and we basically just correlate it with the 1,000 or so pacing sites that we've just done from the model, and from that we can produce a correlation map. And this is just preliminary work. Every week that we go, as Gunnar knows, we're getting a bit better, we're getting a bit closer, we're changing how we chop up the ECGs, how we take them, how we average them, how we produce the correlation map. We're getting closer and closer. This particular example is about 14 millimeters away, which is close, but we want to get a bit closer. So now once we keep moving with this, we keep progressing, we then just need to do the next 20 to 40 points on this patient, and then we just need to do another 24 patients to validate it. And that's what we're going to be keeping busy with in the next few months. So I just wanted to acknowledge the people that actually did the work over at King's, in the lab over at King's, and Pranav, who's involved in a lot of the work as well, who couldn't be here today. And also our external collaborators, particularly Gunnar and his team at Numerical, as well as our clinical collaborators at the Brompton and also at St Thomas's, John and Aldo. Thank you.
Ray, the FDA, very nice talk, Martin. Seems like you have the data both experimentally from the clinic and from the simulations to provide us a little bit more detail about the uncertainty quantification of the conductivity maps that you're generating from the data. For example, if you're pacing at multiple sites, presumably you'll get a different exact conductivity map throughout the heart in your calibration process. So am I right, and can you talk about the difficulty in how you address combining, getting the best estimate, or presumably and hopefully part of your heat map that you're talking about?
Do you mean the pace maps, or do you mean before when we're trying to parameterize the conductivity?
Any of the simulations where you're generating the conductivity maps as a calibration system?
So we're looking at trying different ways, and Manisha, my student here, is looking at that and trying to use the catheter data to try to infer conduction velocity. Is that what you mean from the data?
My understanding is that you're, as others do, is you're generating a conductivity map throughout the heart to match the ECG, and then you therefore have those conductivity values that are derived as opposed to uniform.
So that's what we're looking at. So at the moment we're just using uniform conductivity. So we have default fibers and we have a uniform conductivity. We try to tune it a bit to the QRS. So we've got an overall idea of the conductivity, but the point is that these patients are sick and they've got scar, and so you intrinsically have heterogeneous conductivity. So that's why we're doing the things kind of that Manish is looking at to see if we can. I think it's going to be hard to get that from the ECG. I think potentially during the procedure you could try to tweak your model, you could try to refine it as they move around and they do some of the initial maps, and then you can get a better estimate and you can update what you've done, which is the direction we're heading in, but getting conduction from the map isn't quite straightforward because the ventricle is quite thick.
Yeah, all my question was based on regional conductivity calibrations.
Yeah.
Sorry, never mind.
So when you construct a conductivity map, how many recordings do you take on the average? I mean, how many, 4 or 5 recordings? What is the average surface area of the recording versus the complete ventricular surface area? And where we are like taking an approximation of the conductivity, so what is the range that we are following? So
in terms of the number of points, so it's usually, they're using kind of multipolar catheters, so they're getting quite a few thousand points in terms of the Carter shout, if that's what you mean. Is that?
Yeah, so I mean, like if we have only the, if we have the recordings only at specific points, and now we want a global conductivity map, so what do you recommend? How many recordings should we have, and how much of a surface area covering should we have in the ventricles to have a confident estimate of a global conductivity map?
I don't know. Hopefully we'll tell you in a few months. But I think you need to focus on the area that's important. I think the biggest difference is what's going on in the scar and what's going on in the isthmus. Potentially the conductivity is way away, are far less important. It's that slow conduction in the scar and in the isthmus, which also happens to be where it's really difficult to get measurements from, and it's really difficult to process the EGMs that come out of it in the first place. So it's still a massive problem. I think fitting to the ECG and sweeping over things is probably not the worst thing to do.
Thank you.
I guess I have a question. So the first part of the talk on the DT induction is really interesting. It's really good to see because it's fast. Now we can evaluate how the results changing with the scar mapping and everything. So I think this is my personal curiosity because I've been curious in this for a long time. I haven't been able to get some answers. So how sensitive, like, you know, when you do DT induction, how sensitive is the inducibility to the scar input? Is it like more or less always staying?
It depends if you're talking about the anatomy or the functional aspect of it. So the anatomy, like, absolutely. If you have an isthmus or you don't have an isthmus, you're not going to get a VT or you're not going to get a VT.
Right, so in the same person, you know, depending on your scar thresholding and everything, does that make
It changes completely. You slide, we had another paper that Pranav had actually in Hard Rhythm, and you slide that slider bar for the segmentation threshold and you completely change the anatomy of the scar that you end up recovering. So you completely change the circuits, the exit sites, it all changes. In terms of the functional aspect of it, I don't know if Fiona has some slides on it tomorrow, but it's almost as dependent on the functional aspect of it. So how you assign the properties of the border zone, the differences in APD between the healthy tissue and the border zone determines when you're going to get block, when you're not going to get block, if you're going to get failure to come out the exit site or not. So it's hugely, hugely dependent. And I think that's why we're a bit more interested in just looking at the anatomical side of things rather than combining the functional aspect of it, which you would do in a full-blown monodomain, because I think that's just quite dangerous in terms of actually knowing exactly what you need to know to be able to do that.
And for the pace mapping, also very, very interesting. So for the pace mapping, do you care about so the depth? Like, do you care about FD versus endo pacing? Or?
So I think pace mapping is potentially a lot better because you're only looking at activation as well. So potentially the need to personalize for repolarization is less important because you're just looking for that immediate breakout of that site. But I think at the moment we're just putting kind of standard things into that. But we're looking at, I think one of the really important questions in all of this work is how much detail do you need? Because we could take some imaging data and knock up a model that gives a window of interest for the clinician to look into in 20 minutes and simulation time half an hour. Or you could spend months and months trying to personalize with Purkinje's and all these different things. But how much more do you improve? Because I think ultimately, you know, speaking to the people that are in the lab, I don't think they're ever going to trust a model to give them an XYZ. But if you can just provide a region of interest, that means that when they go in there, they're not mapping the whole ventricle, but they're just mapping this small little subset. I think that suddenly becomes really appealing to them. And I think if you can do that, and if you can do that quickly and robustly, then I think that's potentially going to be the key to it.
You know, current work, is there actually, like, do you do epicardium and epicardium pacing? Do you think it's actually possible to differentiate differentiate?
So most of the procedures are endo, because that's where the access is. Some procedures they do access from the epicardium as well. And I think usually that's one of the restrictions in the clinical way, because they're only restricted to the endo. But in the simulation, we can pace from wherever we want. So potentially we could identify an epicardial VT or intramural VT that they wouldn't be able to access clinically.
Thank you. Well, if there are no more questions, let's ask. Thanks, Martin, again.